Hello, this video has a big idea and an application. So the big idea is conservation laws. The application is to Kirchhoff's current law, Kirchhoff's voltage law. These are two very important ideas uh, in our circuit analysis class. But they're big. So uh, you may have already heard of conservation of energy or conservation of momentum. Let's try to see what do we mean by that. Well, suppose you have some closed system, and suppose there's a certain amount of energy, if you add up all the different forms of energy in that closed system. And if that closed system is the universe, maybe that total amount of energy is zero, some positive, some negative. But for my example right here, let's just suppose there's 100 joules of energy in that room. Then what we mean by the conservation of energy is that if you come back 10 minutes later, the amount of energy in that room is still 100 joules. It may have changed form. You might have had 100 joules of energy stored in a battery, which has now gone to send current through a resistor, which has gone to heat up the room. So maybe you now only have 20 joules in the battery, but then that would mean you have 80 joules of heat in the room. So that's if this room is completely sealed off. No heat or energy can leave the room at all. So in that situation, we'd have this conservation of energy rule. Uh, Same thing with conservation of charge. What if there was 6 coulombs of charge in the room, and the room has no doors, nothing can get in or out, and you come back 3 years later? Is it possible that that 6 coulombs would, when you come back 3 years later, would be only 5 coulombs? That some of that charge was somehow lost? The answer there is no. That would not be possible. So from what we understand of physics, you can transfer a neutron can decay into a proton and an electron plus a neutrino, but the total charge would be zero still, because you started with a neutron which had no charge. The proton has +1, the electron has -1, so they would cancel out. So conservation of charge means the total amount of charge can't change. Okay, there's other conservation laws, and I've directed you to a external video to kind of watch to see some other particle physics conservation laws. I recommend having a look at that so you kind of get the big idea. This is conservation laws. That's the topic. Okay, but before I do this, leave this. Let me look at some other potential conservation laws. Like suppose you lock me in a room. All right, let's take money for an example. Suppose you lock 2 people in a room and they each have $10, and you come back an hour later and one person has $15. How much money does the other person have? I think you would probably and fairly safely conclude $5. If you make that assumption that the total amount of money, $20, still stays the same, this person has 15 and that person has 5, you'd probably conclude that somebody lost a bet, something went wrong for that person. You'd be applying this idea of conservation of money. Now, that principle of conservation of money is not exact. It's not like conservation of charge. Could somebody take a $1 bill and destroy it? So is it possible you could start with $20 and you come back into the room later and there's only $15? Yes. Is it possible you could start with $20 in the room and you come back later and there's $40 in the room? Yeah, but only if they have I guess I'd call that a mint, a United States building that prints money. So our country, of course, does print money. We can make money out of nothing. We do make quite a bit out of nothing. So the idea of conservation of money is only like kind of, sort of, sometimes applicable. Conservation of mass. Well, same problem. Mass can be converted into energy. Conservation of people. Same idea. Sometimes it's useful. So is it always true? No, of course people could die, get born, but uh, we will sometimes have counters on like people entering a store, and you can count people as they go in, count people as they come out, and use the principle of conservation of people to track how many people must be in that store on the inside if you know how many people went in and how many people came out. And of course that assumption, though, again, is assuming that nobody died in the meantime. So we have these other, like maybe these are like kind of conservation laws. Let me look at this one, though. How about conservation of current? Okay, so you've got some electric circuit. Okay, and I've got 2 amps of current. Okay, going around the circuit. Could I come back a day later and there be no current? Like, could I shut the battery off? And if I shut the battery off, is that current conserved? Does it like have to go somewhere? Or can it just stop? The answer is it can just stop. Any idea of conservation of current would be complete nonsense. So this guy is not like even mass and people, where there can be sort of sometimes true. This conservation of current idea is complete nonsense. I can't put enough X's on that right there. Okay. Now, that is different. So conservation of current is not Kirchhoff's current law. Kirchhoff's current law is based on one of these conservation laws. It's based on conservation of charge. So this is saying that the amount of charge, like if you have some node somewhere, and you have currents going in, or maybe some 2 currents going in and 1 current going out, this conservation of charge is saying I can't be creating charge out of nowhere. I can't suddenly have charge in this node where I had none before. So suppose I start with 5 coulombs of charge at that node, and I've got 10 amps coming in here, and I've got 5 amps coming in here. Could I maybe have 0 amps going out? Well, I could, but only if that amount of charge were going up. So if I had 15 amps coming in and no current going out, that means I have 15 coulombs per second of charge entering that node. So that means 1 second later, that would have to get up to 20 coulombs. And 2 seconds later, I'd be at 35 coulombs, and so on. So the amount of charge on that node would have to go up and up and up and up and up. So if I assume that there is no charge, no net charge on that node, then charge conservation says current in must equal current out. I can't get more current going in and the charge being destroyed, or I can't have more current coming out because charge is being created. So Kirchhoff's current law is a conservation law, and it says that the current going into a node has to equal the current coming out. And of course, that's the same thing as just saying that the total of all the currents going in have to add up to 0. So we might write that as the sum of all the currents going into the node have to be 0. That's the same as current in equals current out. Okay. Kirchhoff's voltage law is conservation of energy. So I kind of talk about that a little bit in another video, but since voltage is electric potential energy per charge, then what we have for a circuit is that if an electron or a charge travels around any path in a circuit and gets back to where it started, the total amount of electric potential energy gained or lost to go from point A back to point A is going to be 0. So the since voltage is electric potential energy per charge, then the total sum of all the voltages around that loop would have to add up to 0. So that's also an example of conservation of energy. and we would just write that as the sum of all the voltages adds up to 0. Okay, so Kirchhoff's current law, Kirchhoff's voltage law, big ideas in circuit analysis, but put them in the context. These are conservation laws, and you'll see you'll work with other conservation laws at other points in time. All right, bye.